Okay, so in this video, we are just going to do a quick review for the basic concepts. And also, hopefully this is also a review from your 131 courses. In the lecture, we mentioned that there are two types of variables. So here, let's write down the probability mass function. This is for x following a discrete random variable. And then we also have a PDF where we normally use f of x to denote the density function. And then we talk about the expected value. And you can also consider it as a first moment. And then the formula for the discrete cases is that the x multiplied by the probability mass function, and the support is for all possible x. And then similarly for the continuous case, we also have the expected value expressed as the integral, and then for x multiplied by the density function dx. Okay, and then similarly for the second moment, which is often used for calculating the variance, it just simply by taking the power for the x here and then multiply by the density. And similarly for the continuous case, we have x squared multiplied by f of x and then dx. So for these two, the first moment and the second moment, we can also generalize to the kth moment, which is expected value for x raised to the power of k, and then we have a summation for x raised to the power of k multiplied by the probability mass function. So maybe I can point out that this is for the mass, and then this is for the density. Okay, and then similarly for the continuous case, you just take the integral for x raised to the power of k multiplied by the density and then dx. Okay, and after that, we can also mention a more generalized formulation, which is the expected for a function of x. And then you have the summation of all possible x, and then the function gx multiplied by the probability mass function. So here you can consider this x squared and then x raised to the power of k, or even the x itself. It's a function of x. So gx is equal to x, or gx is equal to x squared, or gx is equal to xk. So these are all the specific case for this, let's say, formulation. All you need to do is just recognizing the g of x is equal to x squared, and then you replace gx here, and then you will end up with x raised to the power of 2 and x raised to the power of k. And then similarly for the continuous case, just for the completeness, this is equal to the integral for all the support of x, and then g of x multiplied by the f of x, the density dx. Okay, so so this is the generalized case, and then the expected value, which is just the first moment, you just consider gx equal to x. So the function input at x and output at x, or a function input at x, output x squared, and then it ends up with all these kth moment. Yeah. Okay, so before we proceed to the examples, let's also mention another very important quantity, which is called the variance. So for the variance, here maybe let's just use, so I'm not going to talk about the differences between the discrete and the continuous case. The only difference is that one is summation, one is the integral. So here we can introduce the formula in the following way. So this is the second moment minus the square of the first moment. Yeah, and then this formulation is also coming from this definition, where we have x deviate from its mu, or here you can consider this as e of x, the first moment, and then taking the square of that. Yeah. So one thing that we show in the lecture is that the right hand side, or this one, is equal to this. So for the completeness, let's also write that out. So here I'm continue expanding the third term here. We will have x squared minus 2 mu x plus mu squared. Okay, and then here the expected value is a linear operation, so we can distribute the expected this operation to each of the terms. So we end up with e of x squared minus, so for the second term, the x is the random variable here. The mu is already considered as constant, like the mu or the mean, the expected value for variables. So that you will have 2 mu as a constant or a coefficient, and then the expected value only going to affect on the random variable x. And then e of mu squared is just a constant itself. And then here you will see that this is just e of x squared, the second moment minus, so this is also ex. Mu is just the ex, the expected value, and also for this one. So you essentially minus 2 copy of mu squared and then added back 1 copy of mu squared, and then you only minus 1 copy of mu squared. But mu is just the first moment, the expected value for a random variable, so that you have 1 copy. You minus 1 copy of mu squared, and that is where this formulation is coming from. So yeah, there are 2 ways to calculate the variance, and then it just depends on whichever is easier for your calculation, and then you can choose. Or where each one has the meaning like that you need, and then you can choose the one that you want to use. Yeah. Okay, that's that. And then maybe now we can proceed to some examples. So for our first example, it's for the discrete case. So we're going to use Poisson distribution, and then we have a parameter lambda here. So when you talk about a distribution, make sure you talk about the support. So the support is that all the non-negative integer, and then for the lambda you also have you need to have the parameter greater than 0. Okay, and now let's also write down the probability mass function, which is the e raised to the power of negative lambda, and then lambda raised to the power of k, and then k factorial. So this is for the case that the x is equal to a particular integer, and then you can plug in to get the probability mass. Yeah. And yeah, so next we are just going to evaluate the expected value and then the variance of x. So this is what we are going to calculate in this example. So let's now proceed to the formula. You have from k equal to 0 to infinity, all the positive non-negative integer, and then you need a copy of x multiply by e lambda x, e raised to the power of negative lambda, x raised to the power of k, and then k factorial. So here I'm just going to write this as k as this is like the random variable here, or maybe just to make it consistent here with your formula, then maybe I just use x, and then x factorial lambda x, and then this one is also x. Okay, so next we are just going to simplify this quantity here. Let's first recognizing that the e raised to the power of negative lambda is not going to affected by this summation here. So we can bring this one in front of the summation, as this is just a coefficient multiplying the whole infinite sum. And then sum of x to 0, infinity. And then we have x multiplied by lambda x, and then x factorial. Now we are going to drop the x equal to 0 case, because when you plug in x equal to 0 for the first term in the summation, this term is essentially just 0, so it does not contribute to any quantity when you change in your evaluation this summation. So what we can do here is to have x equal to 1, starting from 1 to infinity, and then x multiplied by lambda raised to the power of x, and then x factorial. Okay, then another thing that we can do here is to okay, so maybe let me point out one quantity that you have learned in your calculus class, is that this e of x can be expressed as the summation from x equal to 0 to infinity, and then x raised to the power of k, and then k factorial. So as you can see that this term here is very similar to what we have here. So our next step here is just to figure out one way to rewrite this term so that it can look similar to that, and then we can replace with e to the power of x for that change. Actually, I think this should be k. Yeah. Okay. So let's continue from here. So what we can do is first have the coefficient in the front, and then we can leave some space here for now, and then we have the x equal to 1 to infinity, and then we can reduce one copy of x from the denominator by rewriting x minus 1 factorial, and then we'll have lambda raised to the power of x. However, this is not yet close to this formulation, so there's one more thing we need to do. It's just to bring one copy of lambda outside, because this is not this lambda, one copy of lambda is not going to affect it by the summation. So we can bring one copy of that, and now you can recognize that this is very close to this formulation, except that our index is starting from 1 to infinity, and also we have x minus 1 and x minus 1 here. But we can make a change of notation by letting j equal to k minus 1, and then you have the following. So the summation j, so in our case the j is x minus 1. Okay, so when you start from 1 for x, you essentially have j equal to 0, and also you have infinity sum here, and for this one you will have the power up to raise to the power of j, and then j factorial. So now you can see that this is just the same thing here, except that the notational differences. Yeah, so for this one here, you can essentially replace with e raised to the power of lambda, because this is the x here. In our case, x is lambda. So we have e raised to the power of negative lambda, one copy of lambda that we get earlier, and then e raised to the power of lambda. And this will reduce to lambda. So the property for an exponential operation that we use here is that e of a multiplied by e of b is equal to e of a plus b. So our a here is the negative lambda. Our b is the lambda. So when you sum them together, it's e raised to the power of 0, which is 1, and that ends up with one copy of lambda. Okay, so that's it for the first moment. Yeah, maybe I can also point out, if needed, you can also have the ratio of that is just exp of a minus b. Yeah, but basically that's the same. If you have a negative here, you essentially can take the inverse and then it's just a minus b. Yeah, so they are essentially the same, except one is just a negative sign. Okay, so that's for the expected value. Next, we're going to calculate the variance, and then we are going to use the formula for e of x multiplied by e of x squared. So we already have this calculated, then we just need to evaluate the second moment here. Okay, so now let's evaluate the second moment. Summation for x equal to 0 to infinity, and then x to the power of 2 multiply by the probability mass function. X factorial. Okay, so our idea or the procedure is very similar to what we did earlier. So let's bring the e of negative lambda in the front. And let's see. And then we are going to write, okay, x equal to 0 to infinity. And then we write x in terms of x minus 1 and then plus x. So this is x squared minus x plus x, and then it's just essentially x squared. But we're just using this way to make the computation easier. And then you will see that later. X factorial. Okay. And then the summation here is a linear operation as well, so let's distribute the summation. So x minus 1 e lambda x, and then x factorial, and then you have a plus another copy of coefficient summation x equal to 0 to infinity, and then you have one copy of x from here multiply by that. Okay, now you can recognize that this term here we have already seen earlier, which is just the first moment that we evaluated. So we know that this is going to be lambda already, so we don't need to worry about that. All we need to do is just to work on the first term, and then don't forget to add this lambda back in our formulation. Okay, so now let's just focusing on the first term. So here we have e negative lambda summation x equal to 0, and then we can drop the first two cases. So when x equal to 0, this is 0. When x equal to 1, this is also 0. So let's change the index starting from 2. Okay, so also let me leave some space here. Change the index equal to 2 from infinity, 2 to infinity. And then we also replace the denominator as x minus the 2. And then sorry for copying. So there's no longer the e of negative lambda here. So you only have lambda on the top. Yeah, and then you have x raised to the power of x. But what we can do here to complete the number here is that we can remove 2 copies of lambda and then bring the 2 copies of lambda in front. So this is also what we did earlier in the when we calculate the first moment. And then you have 1 copy of lambda from here. And next, let's also call j equal to k, or in our case, x minus 2. So we have e negative lambda square summation from j equal to 0, again to infinity. And then you have lambda raised to the power of j factorial plus 1 copy of that. You will have e negative lambda square e positive lambda plus a lambda. So you have a lambda square minus plus a lambda. Okay, so this is only the second moment. What we really want is the variance. And this is equal to e of x square minus e of x square. And you have lambda square plus lambda. This is the second moment, but you also need a square of the lambda, and you end up with 1 copy of lambda. So for Poisson distribution, the first moment is equal to lambda, and then the variance of a Poisson random variable is also equal to lambda. Okay, so this is for a discrete random variable, or specifically x following a Poisson distribution. Next, we are going to perform the same procedure and then let x following a exponential distribution. So for this one, we have x greater than 0, and then also this x is in for real number, like continuous number. It does not has to be like 0, 1, 2, all the integer. And then for the lambda, we will have this greater than 0. Let me okay, so now we are going to calculate the e of x, and then e of x square, and then the variance of x. So for a continuous case, we need to, or maybe let's first write down the probability density function. So what we have is the lambda multiplied by e negative lambda x. So this is the PDF for a Poisson distribution, for a exponential distribution. Okay, now let's evaluate the expected value. We have the integral for, let's write it more specific. So from 0 to infinity, to evaluate this integral, x multiplied by lambda e negative lambda x dx. Okay, so one thing here is that you have one copy of x here and then one copy of x here. So to evaluate this kind of integral, something that you learn from your calculus class is that you can do it by integration by parts. So the idea is that you have a integral can be expressed as let me write it, the formula. So you have a v let's say u dv, and then you can write it as u multiplied by v minus the integral of v du. So this is something that we're going to do. So by looking at this, we can set u equal to x, and then dv is just the lambda multiplied by e negative lambda x dx. Okay, then for du, you just have dx, and then for v, you essentially take the integral of this, and this is equal to, there's a negative sign here, e negative lambda x. So you can also verify by taking a derivative with respect to x for this term here, and then you should get this term as well. So when you take the derivative, you have the negative sign canceling out, so it's a positive here, and then you also have one copy of coefficient lambda in the front, and then this term stays the same. So these four terms can be specified in this way. And now let's just complete the right hand side here. So let's uv negative x e negative lambda x. So that's u multiplied by v, and then integrate, and don't forget there's a minus sign here, and then v du. Okay, so there's another negative sign here from the v, and then du is just dx. And then for now evaluating this integral here, let's keep the negative sign here, and then you should have 1 over lambda e raised to the power of negative lambda x. Let's just double check. So if you taking the derivative of that, you will have a negative sign in the front, which is this negative sign, and then this lambda will canceling out with this coefficient, and then you have this term. Okay, so this is our final form, and we need to evaluate the integral for x to from 0 to infinity. Okay, so for that, let's just write down one more line to make it easier. So you have a negative, more specifically, write it in the form of fraction. You have a negative x in the numerator, and then for the denominator, it's just lambda x. So I'm just rewriting the negative sign into the denominator. And then similarly, you have 1 over lambda, also multiplied by 1 over e lambda x. So the tricky part here is that how you're going to evaluate this from 0 to infinity. So one problem is that when you plug in the infinity to the first term, you essentially have a fraction of infinity over infinity. That is not, you cannot evaluate that kind of a quantity. So you're going to use the L'Hopital rule to calculate the limit for this. So the idea is that you need to take the derivative for x go to infinity. So you want to evaluate this specific, but you cannot evaluate infinity over infinity. So you take the derivative for the numerator and the denominator. You will end up with -1, and then lambda multiplied by e of x lambda x. And now you essentially have a -1 divided by a very large number that will give you a 0. Okay, and then for the second term, when you plug in the infinity, you just have 1 over infinity, and this will goes to 0. So let's continue for this equation here. When you evaluate the limit of this go to infinity, you will have a 0 as we did here. And when you plug in the infinity to the second term, you will also have a 0. And now you need to minus the difference when you plug in x equals 0 in this. And when you plug in x equals 0, this is just a 1, and this is 0, so you have another 0 here. And now when you plug in 0 for the second term, this is a 1, so this becomes a 1, and you only have one copy of 1 over lambda. And then this is a positive 1 over lambda. Okay, so just to circle back or to remind you what we're doing here, this is the expected value for an exponential distribution. Next, let's find out the second moment. Okay, so for again, just by taking the formula, x squared f of x dx, or maybe just write it okay. So again, we need to do integration by part. So let's set it equal to x squared, and then dv is just lambda e negative lambda x, and then du is just 2x dx, and then v, this is something that we already have earlier, so negative e negative lambda x. Okay, so now we're going to use these 4 terms to construct to calculate this integral. So uv is negative x squared e negative lambda x minus a integral for, let's see, v du. So v is a negative e negative lambda x, and du is just 2x dx. Okay, so let's further evaluating this integral. Actually, let's see. So this part is actually something that we already did. So let me bring the 2 in the front, and also let me change the plus here. So does this remind you of am I missing something? So we need v du. Okay, so this is not yet what we have seen earlier. What I'm trying to say is that we actually want to reuse the information that we get when we're calculating the first moment. So as you can see that this one, comparing to the expected value here, we are only missing a lambda here. So, and also the lambda is not going to affect it by the integral. So what we can do here is that we can do it by construction to make our evaluation simpler. We'll take the integral. We have one copy of 1 over lambda, and then we added a one copy of lambda here. So this is by construction for the purpose to mimic this one and to ease our computation. So as you can see that when we multiply a coefficient divided by a coefficient, this integral here ends up with the expected value. And this is just 1 over lambda, and this is just this term here. It's just the expected value. Okay, so we get this equal to lambda to simplify. So when we construct it in this way, we don't need to evaluate this integral anymore, and that is how it can ease our computation. Okay, so by that, let's finish the equation here. You just have 2 copy 1 over lambda, and then the expected value is also a 1 over lambda. So you have a 1 over lambda square. And then you just need to evaluate this whole term, x equal to 0 to infinity, because this is just a constant term. Okay, so let's further rewrite this as a fraction, negative x squared over e lambda x equal to 0, x equal to infinity, plus 2 over lambda squared. Okay, so again, when you want to evaluate this limits from go to infinity, and you will also run into the problem that you have infinity over infinity. So you need to use the L'Hopital rule again. So you will have x go to infinity, negative 2x over lambda e lambda x. However, this also ends up with the negative infinity over infinity situation. So you need to do it again. You will end up with 2x, negative 2 over lambda square e lambda x. And now when you evaluate this to infinity, you have a infinity in the denominator, and then this will end up with 0. So let's back to this formulation. You will have 0 and then minus when you plug in 0 here, and this will reduce to 1, and this will reduce to 0, so you have another copy of 0. And then don't forget this is a plus. Okay, you will have 2 over lambda square, and this is the second moment that we evaluated. So we started with the second moment. So our goal, our final goal, is to have the variance of x, which is e of the second moment minus the square of the first moment. And then you will have 2 over lambda squared. And let's see what is the first moment. The first moment is lambda, 1 over lambda. So you will have 1 over lambda squared. And this is just 1 over lambda squared. And then you have 1 copy of lambda squared. So for exponential distribution here, which is a continuous random variable, which has this formulation for the probability density function. The first moment, or the expected value, we use the integration by part, and then we end up with 1 over lambda. And then for the second moment, we also use the integration by part, and then we also, by construction, using the information that we did for the first moment to replace the second term. So we don't need to evaluate this integral anymore. And then we use the L'Hopital rule twice, ends up with the second moment, and then we use the formula to calculate the variance of x. Okay, so I think maybe I will end this this lecture by just writing or provide you some more formulas that we often see or we often use, particularly for the covariance between two random variables. So yeah, so I hope this is also a review from your 131 lectures. So for covariance of two random variables x and y, the formula will be the expected value for x multiplied by y minus e of x and then e of y, which is the first moment for random variable x and the first moment for random variable y. And then particularly for this expected value x and y, this is equal to the joint. And yeah, maybe we can talk more about that in the later lecture. So this is the joint probability density function, dx and dy. Okay, that's that. And then there's also a something called correlation for x and y, which is highly related to the covariance, which have the following equation. So the variance of x and the variance of y, but you need to take the square root, which is essentially the standard deviation. And sometimes people also use rho for this correlation thing, and this rho is some number in between +1 and -1. And later we will also using this equation to develop some more result in the later lectures. Okay, then let's also provide some more formula here. So we have covariance of ax plus b and y is equal to a of covariance random variable x and y. So intuitively, when you shift a random variable by a particular constant, so a and b are constant here. So when you shift a random variable by a particular constant, it will not change its covariance or its variance also, because the variance is just how spread out the random variable is in the probability distribution. But if you just shift all the variables by amount of b, the variance does not change, although the mean or the expected value will change. And later we'll talk more about that. Yeah, but that is the case here. And the also for covariance, let's say x plus y, two random variable, and then with a third random variable. This is equal to the covariance of x and z, and then plus the covariance of y and z. Okay, and that's that. And then also, just to mention what we have said earlier, ax plus b for the variance, and this is equal to maybe let me write down okay, so let me put it here as well. So the covariance of x and the x here. So you can see that when you have x and x here, when you consider y as the x as well, you essentially have a second moment minus the square of first moment. So that's why the covariance of itself is just the variance of x. Okay, now I just want to use this idea to introduce the idea for when you scale a random variable and then shift a random variable. So I can use the idea of the covariance back here. So this is covariance of x equal to variance. So now I'm going to use the opposite direction. So you can consider this as the covariance of ax plus b, and then ax plus b, like itself. Okay, and then this, you can use the formula here. So you will have two copies of a. So yeah, so for example, if you have ax plus b or ax and by, you will have ab covariance of x and y. So you have one scalar here and one scalar here, and then you end up with two copies of them. So you have a square and then covariance of x and x, and this is just the a square variance of x. And again, the constant term is not going to affect your variance. So you have this equation or this equality as well. And let's see, I would like to end this by having variance of x plus y. So two random variables here. This is equal to, also just using the idea for covariance here, you can consider this as covariance x plus y and then x plus y, and you will have and then I'm going to use this one as well. You will have four terms. So covariance of x and dx, and then you will have covariance of x and this y, and then you will have covariance of y and this x, and then you will have the covariance of y and y. So different combination. So you will end up with variance of x plus variance of y plus 2 copy of covariance x and y. And also here, let's also point out that covariance of x and y is equal to the covariance of y and x when you change the order. You can also see this from this equation here. So when you change the order, it does not change the quantity. So x and y, covariance of x and y is equal to covariance of y and x. Okay. Let's see what else. Okay, so maybe you can also mention that this is generally the case, but sometimes there are some independent random variable. So you will have variance of x x plus y, but they are independent. So what you have is variance of x plus y, but there will be some differences in the covariance term. So let's plus 2 copy of covariance. So now we can circle back to the formulation of the covariance here. So if x and y are independent, then the expected value of their product can be decomposed into e of x multiplied by e of y. This is true only when x and y are independent. Most of the time, this is false, but only when this is independent. Okay, and then you will have the e of x multiplied by e of y. You will see that this term goes to 0. And then for independent random variable, the sum of them is just the variance of the sum is the sum of the variance of the individual. But this is only when they are independent. Okay. So let's see what else. I think I have provided many formulas for the quantity of interest for a random variables. So for the expected value, the second moment, and also the variance, and then we talk about the covariance between two random variables. Okay, so I think this will serve as a quick review or for our week 1 for stats 132.